Hi, welcome back. Suppose we're given the following polynomial function centered at x equals a. So in Algebra 2, we learned how to write a polynomial function. And you might remember this as a polynomial function could be written as a plus bx plus cx squared plus dx cubed, and so on and so forth, right there. And what we're going to do differently is we're going to set up our polynomial function, in this case, centered around x equals a. And we're, instead of using a, b, c, and d, because that can get kind of lengthy for us, we're going to use c1, c0, c1, c2, c3 to represent our coefficients, like we did up here in our polynomial function. And since we're centering it at x equals a, we're just shifting over our x coordinate one a units to the left or right. So instead of bx, it would just be like cx minus a to represent that shift right there. So this is our polynomial function. Now what we want to do today is come up with a technique to find how to find the coefficients in front of all of those. Is to find these coefficients. And notice we went all the way down to this generic term right here, where to c sub n x minus a to the n. So we can do this generically as well. And if you notice, it just keep going, but we're just going to stop here at the generic term. So all we want to do today, our goal is to find the coefficients. That's our goal, to find the coefficients. And in doing so, we're going to generate a very important formula for it. It's called a Taylor polynomial. So the first thing to find the coefficients is I can first let x equal a. Just let x equal a here. And if we were to solve this, we would get f of a equals c naught. Notice every other term is just going to become 0 because we get a minus a minus a minus a. So we just get a whole bunch of infinite number of zeros there. So we can therefore say f of a is c naught. So easy enough. So I just found my first coefficient. The first coefficient is the value of the function at whatever a is. Next, now we need to come up with a way to find the other coefficients. So to do this, we're just going to use a skill that says, hey, if I can get rid of my c here, my c naught, I can find c1. So to do that, we're just going to take the derivative. So let's take the first derivative. Find the first derivative. And of our function, we would just get f prime of x equals, well, c naught's a constant, so that just becomes 0. c1, now if I look over here, if we look over here, if I take my first derivative, notice the derivative there is 1. If I bring down that power, I'm just going to get c1, and we're left with, in the inside, is x minus a. Whoops, sorry, that derivative, sorry. And that derivative of the inside is just 1. There we go. So times 1, like your chain rule right there. So times 1 plus, and if I keep going down the road, we just get 2 times c2. The derivative of the inside is just x minus a plus, what do we get here? The next one, we're just going to get 3c cubed x minus a squared plus keep going 4, oops, not times c4 x minus a cubed. Again, the derivative of the inside is just 1 plus, and we just keep going and going until we get to the very end where we're down here. We would just get n times c sub n x minus a to the n minus 1. And it does keep going. So I can find c1 now, like we did up here, like we did for the first one, if we now find f prime of a. So again, if we let x equal a, we would get f prime of a equaling, we would just get c1. And again, all these other terms just become 0. So c sub 1 equals f prime of a. Because again, all those other terms just become 0 plus 0 and plus 0 at the very end. So therefore, we can say f prime of a is c1. So c1 is just the value of the first derivative. And we just keep going. Hold on here. Let me get out of here real quick. It's kind of paused on me. There we go. I don't know, it just keeps pausing at me, so sorry about that. So now we can just keep going, and now let's see here. So we found C1. So now we got to find C2. How can we find C2? I can take the next derivative. So we're going to take the second derivative now. So we're going to go ahead and find the second derivative. So let's go ahead and do that. Well, our second derivative just becomes, well, C1 is just a constant now, it's just 0. So when I take the derivative over here, the derivative here, there's a 1 there. I'm just going to get 2 times 1. I'm going to write this out. That's 2 times 1 this time. So we get 2 times 1, because I want you to see a pattern. C2, the value of the derivative of our inside is just 1, so I can multiply that by 1. Don't need to, though. And I just keep going. Plus our derivative over here, bring down our 2. We're going to get 3 times 2 this time. So we get 3 times 2 times C3, and we get x minus a to the first. And I just keep going. The next one is 4 times, and over here, bring down that 3, so we get 4 times 3 times C4, x minus a squared. And we just keep going, plus until we get to the very end here, and we're going to get this n times n minus 1 times c sub n x minus a to the n minus 2. And it does keep going, going, and going. Now, hopefully right now you kind of see a pattern going on here, but if you don't, that's okay. We'll get to it in just a second. So just like before, we are going to let x equal a. If we let x equal a here, we will get the second derivative at a. Let me go and zoom out here. And that's going to give us just 2c2. So we're going to get this what? 2 times c2 plus, and again, I'm going to leave this as, this just becomes 3 times 2 times, of course, that just becomes 0, plus all these other zeros again. Remember, this goes on forever. So therefore, we can say, we can now solve, we can say f double prime of a equals 2c2, or that c2 equals the second derivative at a divided by 2. And we just keep kind of going with the pattern. So let's do the third derivative, and we'll see if we can come up with a pattern here. So now we're going to go ahead and take the third derivative, just like we've done before. So we're going to go ahead and find the third derivative of x. Yes. So we would get f triple prime of x. And over here, up here, our derivative just becomes 0, because that's just a constant. So we get 0 plus, now over here, let's see if we can see the pattern. When we drop this 1, we're going to get 3 times 2 times 1 this time. So we get 3 times 2 times 1, C3. The derivative of our inside is just 1. So right away, you kind of notice, look, up here it was 2 times 1, 3 times 2 times 1. You should kind of notice that this is almost like a factorial growth, and that's really what it is. So the next one we would get over here, and when we take the derivative here, we would get 4 times 3, drop the 2, so we would get 4 times 3 times 2 c4 x minus a to the first, plus, and our generic one, dot, 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 is going to be n minus 1, n minus 2, x minus a to the n minus 3 this time. And it does keep going, plus, dot, dot, dot. And like we did before, just let x equal a. And we can get our value of our third derivative of a is 3 times 2 times 1, C3. And again, all the other terms just become 0. So therefore, we can say C3 is just going to be this third derivative of a over 6. And it's at this point we should kind of recognize a pattern. If you notice, we keep getting these little factorials right over here. We're just going to get a bunch of these little factorials. So that's going to come up with our little generic term right here. And this is what we call the Taylor series. So what we can say then is the coefficients just become the value of some derivative at a over that n factorial right there. And that's what we kind of see right up here. If we look at the first one, the first derivative was just the first divided by 1 factorial. The second derivative became, remember we had this 2 times 1, became over 2 factorial. Our third derivative just became over 6, which is just a 3 factorial. And this is what we call and this is how we generate the Taylor polynomial. And that's what we call it. And if we look at the generic part of it right over here, if we look at this part, this right here is our Taylor. So we can say that the Taylor polynomial is generated by looking at the nth derivative of a over n factorial. And notice we still have that x minus a right there because we have to have our polynomial function anyways, and that's just going to be to the nth right there. And this is how we generate the Taylor polynomial right there. All right. Hope you enjoyed the video. See you later.